In this video lecture, we are going to be talking about pressure. Remember, there are four main factors that affect how gases behave. The first one that we talked about was temperature. Today we are continuing on with pressure. And before we start, I just want to go over a couple of ground rules for this video lecture. So in order for you guys to be the most successful, I would love for you to stop the video at any time. If there is a bullet point that you need to go back to, feel free to reverse. This is on YouTube, so it works like any YouTube video. If you need to pause, go back again, feel free to do so. The next thing is that I do need you to follow along on the note sheets. This is crucial because these are the only notes that you are going to get on this topic. Lastly, when I go into the example problems, I have everything typed up, in my slides, but I need you to write down all of the work in the order that I put it up on the PowerPoint, because you need to be able to complete the example problems and complete problems like the example problems. So if you write down all of the work, you'll just be more successful when you have to do this on your own in your homework. So with that being said, let's go ahead and get into the notes. Okay, so what is gas pressure, or what is pressure and how does it affect gases? Well, the first thing that we need to keep in mind is that gas particles are in constant random motion. This is something that we talked about the last time that we took notes, and it's important that we keep this main idea in our brains today as we go forward. So the motion of those gas particles means that particles are constantly colliding with each other and colliding with the walls of their container. Remember, gas particles act like kindergartners. They're super chaotic and they're running all over the place, and you never know what they're going to do next, but they're always moving. So these gas particles are constantly colliding with each other and with the walls of their container. And what that means is those collisions is what pressure is. So pressure is exerted by the particles when there are collisions. It's like, let's think of another definition of pressure. So maybe you think of pressure as pushing down on top of your desk. So everybody take your hand and push down on the table in front of you. Right now, you are exerting pressure on the table, and the table is actually exerting pressure back. So when particles collide, or push on, the walls of their container or the desk, for example, particles are exerting pressure. If the more collisions there are, the greater the pressure is, right? The more collisions there are, the greater the pressure is. So if there are fewer collisions with the particles and with the walls of the container, there would be less pressure. Remember that we think of standard atmospheric pressure to be 1 atmosphere, or 1 atm. And then on the side here, I have this example of squeezing a basketball. Now, if any of you have ever played basketball or soccer, or football even, anything with a ball sport that's inflated, maybe you remember squeezing the ball before going to play just to make sure that there was enough air in the ball. Well, when you squeeze a basketball, what you do is you are creating a change and trying to feel how the air particles respond to the change. So if you are pushing on the ball and you don't feel a lot of give, that means there are lots of particles that are pushing back and the ball is full of air. But if you squeeze the basketball or the soccer ball or whatever, and it really squeezes in tight and it's super deflated, that means there wasn't a lot of air particles in the ball to create pressure. There wasn't enough collisions, and so you were able to squeeze the ball a lot smaller. So if you want to write anything down sort of about that example that you think would be helpful for you to refer back to, go ahead right now. Otherwise, we are going to continue moving forward in our pressure notes. How do we measure pressure? Well, we use a barometer. A barometer is what measures pressure exerted by the atmosphere. And the barometer was developed by a man named Evangelista Torricelli, and he had, similar to a thermometer, but it's a device that has a column or a little skinny tube of mercury in the center, and the height of the mercury determined what the pressure in the atmosphere was. And that's actually why the first known unit for pressure was millimeters of mercury. Right? mmHg stands for millimeters of mercury. Now, if any of you have ever gone to the mountains, maybe you've experienced a pressure difference. So when you go high in altitude, it gets harder to breathe. And that's because there's less oxygen in the air, but really there's less gas particles in general because we are feeling less pressure from the atmosphere. In the same sense, if you go really, really deep into the ocean, maybe if you've gone scuba diving before, you can feel that pressure increase as you go further and further down underwater. You can feel the weight of the water pushing on you and the weight of the atmosphere above that. So based on your altitude, how high you are on the earth, you're going to feel a different pressure. Now, St. Louis is about at sea level, so we are pretty much right around that 1 atmosphere mark. But lots of places have totally different atmospheric pressures. And it's definitely, if you're interested in that sort of thing, definitely take the time and look up some examples on your own. These days, we don't necessarily use millimeters of mercury all the time to measure pressure. There are lots of other pressure units. So what I have listed here are a couple of conversion factors or ways that we could convert between 2 different pressure units. So we're familiar with 1 atmosphere. That's the standard atmospheric pressure that you were taught in this unit. And 1 atmospheric pressure, or 1 ATM, is equivalent to or the same as 760 millimeters of mercury. And like I said, millimeters of mercury is that unit that was originally developed by Evangelista Torricelli. In the US, what you see a lot of times is PSI, or pounds per square inch. There are 14.7 PSI for every 1 atmosphere, or 1 atmosphere equals 14.7 PSI. So if you're thinking of tire pressure, the unit for that is usually PSI. And lots of machinery, manufacturing, engineering type environments will use PSI as the pressure unit. The last pressure unit that we're going to talk about is called kilopascals. There is 101.3 kilopascals for every 1 atmosphere, or maybe you want to read it as 1 atmosphere equals 101.3 kPa, or kilopascals. And this is the standard international unit. This is the SI unit that scientists all around the world use. We're not going to run into it a lot in the US, but it is important to know how to convert to this unit because that's the standard pressure unit, in Europe and lots of other nations. So we're going to learn how to convert between all 3 of these different pressure units. So on your notes, we are going to first convert 2 atmospheres to PSI. And in order to convert between these 2 units, you need to have a conversion factor. And that conversion factor is what's listed there in the parentheses. We saw on the last slide that 1 atmosphere equals 14.7 PSI, but you could easily switch that around and say 14.7 PSI equals 1 atmosphere. Those are the same thing. So the first thing that we're going to do is write down what information was given to us. So in the problem, it says 2 atmospheres. And that's the sort of first thing. So on the left, write 2 atmospheres, and that's sort of over nothing or over 1. And that 1 underneath 2 atmospheres is just a placeholder. No unit goes there. So think back to stoichiometry, right? Where this is set up very similarly in that we are trying to cancel out units to change to new units. So the 2 atmospheres goes first because that's the problem. That's the given information in the problem. And then we multiply it by this fraction, this 14.7 psi over 1 atmosphere. The trick to figuring out which value goes on the top, or the numerator, and which value goes on the bottom, or the denominator, is looking at the units. So we started in ATM, or atmospheres, and over there where it says 2 ATM, that's on the top of a fraction. So if we wanted to cancel out the atmosphere units, we know that we are going to have to have ATM on the bottom of the next fraction, because something that's on the numerator and something that's on the denominator will cancel out with each other. So in order for ATM to cancel out, they have to be on opposite sides of the fraction bars. And then on the top would be the 14.7 psi. And if you're wondering where I got the 14.7 psi, or the 1 atmosphere, that's directly from the conversion factor that's listed in the parentheses above, right? So this is a normal unit conversion. So now what we would do is multiply 2 times 14.7 and then divide by 1. And we don't have to divide by 1 because anything divided by 1 is itself. So the answer is just 2 times 14.7, or 28.4 psi. We know that we ended up in the correct units because both of those atmospheres canceled out, right? They both have red lines through them, which means we are no longer in that unit. We are just in psi. And so it seems like we were successful in converting from 2 atmospheres to psi. But let's try another one with a different unit. Let's try converting 1.76 atmospheres to kPa, or kilopascals. We're going to set this problem up in a very similar way. We are going to start with that 1.76 ATM on the left side, and it's going to be over 1, right? That 1 is just a placeholder, right? The 1 is just a placeholder. Then we're going to multiply by another fraction. Again, we want to be able to cancel out of the atmosphere unit. We are trying to go to kPa. So in order for the atmospheres to cancel out, they have to be on opposite sides of the fraction bars. And it looks like they are. So those 2 atmosphere units are going to cancel out, and we're going to be left with kPa. So again, now that we have converted these units, all we have to do is multiply. In this case, we're multiplying 1.76 times 101.3. And hopefully, if you're following along, you got 178.288 kPa. And in this case, I'm going to go ahead and round that to I'm going to round that to 178 kPa. Again, I know that kPa is the correct unit because A, the problem asked me to go to kPa, and I double checked that my units canceled out appropriately in the problem. That's what those red bars are, canceling units. All right, so there's a couple of examples. We're going to keep going with the examples this time. I want you to go ahead and try it on your own. So go ahead and pause the video and see if you can convert 608 millimeters of mercury to atmospheres. So this time we aren't starting in atmospheres. We're starting in a different unit and we want to go to atmospheres. So think about how that affects which units are on the top versus the bottom of your fraction. If you didn't pause the video, that's okay. We are going to just jump right in and continue figuring out these problems. So 608 millimeters of mercury is what was given to us in the problem. So that's going to be the first number that we write down. And again, we're going to put that over 1 because putting something over 1 is meaningless, right? Anything divided by 1 is itself. And so that 1 is just a placeholder. Then we are going to set up another fraction, right? And this time, atmospheres is on the top. The reason that atmospheres is on the top is because we needed the millimeters of mercury, or the mmHg, to cancel out. We needed those units to cancel out. So if you notice, right, 608 mmHg, one of those units is on the top and the other one is on the bottom. So those units are going to cancel out leaving us with just atmospheres as the unit that we want to be in. Again, if you are struggling to remember where we get the 760 mmHg or the 1 atmosphere, that's from the conversion factor listed in the parentheses above the problem. So now we have to multiply these two fractions together, the 608 over 1 times 1 over 760. But again, those ones are sort of meaningless, so what we actually need to do in this problem is divide. We need to take 608 and divide it by 760. Remember, those bars in the middle are division lines, right? This is like setting up fractions and multiplying fractions. So we would take 608 times 1, right, and the 1 doesn't matter, and then we would divide by 760. So if you want to take a little shortcut, you can just do 608 divided by 760, and you should get 0.8 atmospheres. Let's do one more example. This time we are converting 16.9 psi to atmospheres. And again, the conversion factor is given in the parentheses. We're going to start with the value that the problem gave us, that's 16.9 psi. We're going to put it over 1. All right, the 1 is just a placeholder. So when it says 16.9 psi over 1, the 1 is just telling you that there's no unit that goes on the bottom. Then we set up that next fraction where it says 1 atm over 14.7 psi. And the order or placement of those units is important so that we can cancel out of psi. We do not want to be in pounds per square inch. We want to be in atmospheres. So in order to get psi to cancel, 1 has to be on the top and 1 has to be on the bottom. So now those units are going to cancel out. ATM goes on the top. And then similarly to the last problem, we're going to do 16.9 times 1 divided by 14.7. Right, because we don't have to use the multiplying, we don't have to multiply or divide by 1 because we would just get the same answer. So you would get 16.9 divided by 14.7, and then you would get 1.14965 atmospheres, or in this case, I'm going to go ahead and round it to 1.15 atmospheres. You will be expected to know how to convert between these two units, and it is going to be on the quiz that we have next week. All right, so you will be expected to convert between these two, or between all of the pressure units. If you need to go back in the video and repeat my explanation of any of these problems, please feel free to do so. Otherwise, I'm going to go ahead and go into the next topic. At this point in the PowerPoint, you need a new note sheet. Right? There should be 2 separate note sheets, one for just pressure and 1 set of notes for this Gay-Lussacs Law section. So you should have a new note sheet out in front of you. Now we're going to talk about what's called Gay-Lussacs Law. This is one of the gas laws, right? The gas laws that maybe you've heard about. Maybe you've heard about Boyle's or Charles' law in the past or on the vocab that you had to do over spring break. But Gay-Lussacs law is one that relates temperature and pressure. It's also known as the temperature-pressure law. And what Gay-Lussacs law states is that temperature is directly proportional to pressure when volume is held constant. So this law relates temperature and pressure. And I bolded directly proportional because that's the important part. If something is directly proportional, that means that if one changes, right, let's say temperature changes, pressure is going to change the same way. Right? So if temperature goes up, pressure is going to go up. If pressure goes down, temperature will go down. That's what it means to be directly proportional. But this law only works when temperature is in Kelvin. Remember that Kelvin is the only temperature unit that is directly proportional to the average kinetic energy of gas particles. And so it's the only unit that we can use to describe gas behavior. So this is like the most important note that you could write down, that Gay-Lussac's law only works when temperature is in Kelvin. Go ahead and write that down and bold it, star it, underline it, highlight it, do whatever you need to do to make sure that you remember that we can only use this law when temperature is in Kelvin. And like I said before, that directly proportional piece means that when temperature increases, pressure increases, or vice versa, right? If temperature decreases, pressure decreases. Right? They go hand in hand. If one changes, the other one changes in the same way. So if temperature was doubled, we would expect the pressure to double as well. Now, why is that? Like, can we come up with any sort of explanation that we know of based on what we've seen about how gas particles behave to explain this law? So let's think. Of course, I'm just going to walk you through it, and I'm not there to do this interactively with you. But try and give yourself a second to think about this. If the temperature was to increase, how would that affect the particles' behavior? If the temperature were to increase, how would that affect the gas particles' behavior? Hopefully, you're thinking to yourself, or maybe thinking out loud, that if temperature increases, then the particles start to move faster, right? If it goes up, then the speed of the particles goes up as well. And we know that volume is constant, right? Because that's what it says for Gay-Lussac's law, is that volume is constant. So if the particles in a box, let's say, are moving faster, does that mean that they are colliding with the walls more or colliding with the walls less? Hopefully, again, you're thinking along the same lines as me, that if the gas particles are moving faster, then that means that they're hitting the walls of their container a lot more, and they're colliding with each other a lot more. And if they're colliding with each other more and colliding with the walls more, then they are exerting more pressure on the walls of their container. So the temperature increased, which made the gas particles speed up, which made the pressure increase. If we do the opposite, let's say the temperature goes down, and now the gas particles aren't moving as fast. They're moving pretty slowly. So now they aren't hitting the walls of their container a lot, right? And because they aren't hitting the walls of their container or hitting each other a lot, then the pressure that they are exerting goes down because they aren't creating those collisions. So this is sort of the thought process that you need to go through when you are trying to figure out how different factors affect gas behavior. Right? When temperature increases, particles move faster, which makes them collide more with each other in the walls, thus increasing the pressure. This is the type of answer that I would expect to see if we ever did a short answer or sort of fill in the blank type of question on a quiz or test. You can actually put numbers to Gay-Lussac's law, and on your note sheet, you'll see the formula. It says P1 over T1 equals P2 over T2. And this setup is what's known as a proportion. So a proportion sets two things that are equal to each other, and we can solve for an unknown variable if we know the other three pieces of information in this case. And so when we do problems like this, what you're often going to see is word problems. But I don't want you to freak out, because I'm going to teach you how to pull out all the information from the word problems and how to be successful when completing these types of problems. So in example 1 here, in the top box on your note sheet, it says at 273.15 Kelvin, helium gas is in a metal sphere, right, which just means it's in a metal ball. And that ball or sphere has a pressure of 1.00 atmospheres. When the temperature increases to 290 Kelvin, what is the pressure in the sphere? So if you need to read that to yourself again, go ahead. But the first thing that we're going to do to sort of attack this problem, find the variables, right? We need to find all the variables from the word problem, and then we also need to make sure that all of our temperatures are in Kelvin. Because remember, we cannot do any of these math problems unless the temperatures are in Kelvin. Let's go ahead and find the variables from the word problem. Let's repeat it. It says at 273.15 Kelvin. Okay, so that's a temperature, right? You should be able to recognize the K unit is a unit of temperature. And it looks like it's already in Kelvin for us, so we don't have to do any converting. So that's the first variable, 273.15. Okay, so that helium gas at 273.15 Kelvin is in a metal sphere, and that metal sphere has a pressure of 1 atmosphere. So those two values go together, right? So in this case, we're going to say that the temperature, 273.15, is P1, and the pressure is pressure 1 is 1.00 atmospheres. Those two values go together, right? It says that gas at this temperature has a pressure of 1 atmosphere. So those go together. We're going to say that the pressure is P1 and the temperature is T1. And then when the temperature increases, right? So when you see the word increases, you're thinking, okay, now a change has been made. So now we're talking about the second scenario. So the temperature increases to 290.00 Kelvin. Right? So that's going to be our temperature 2. And then it asks us, what is the pressure in the sphere? So I'm going to go ahead and circle the variable that I don't know, or the variable that we need to solve for. And that's the first step in being successful with word problems, is finding all the information that you need and labeling it. So on your paper, if you didn't already label these values as P1, T1, P2, or T2, I need you to go ahead and do that right now. Step 2, we're going to plug the variables into the formula, which is why it's important that you wrote down somewhere which value was what variable. Because if you didn't write it down, then this can get very confusing. And this is the step that most students will get tripped up, that will lead them to an incorrect answer. So make sure that you plug the right value in for the right variable. But once you plug all your numbers in, you should get something that looks like this. 1.00 atmospheres over 273.15 Kelvin equals P2, right? Remember that pressure 2 is what we're solving for, divided by 290.00 Kelvin. We've got all of this together. And if you think back to math class, the way to get rid of this proportion is to cross multiply and divide. So we are going to take those diagonals. That's what cross multiply means. We're going to multiply across the equal sign on the diagonal, and you should get 1.00 atmospheres times 290 Kelvin equals, and then you do the other diagonal, 273.15 times P2. So that's how you cross multiply. And then now we just have an algebra problem. We need to solve for P2. So in order to get P2 by itself, we need to divide both sides of the equation by 273.15. So this next line that I just put up on the screen, all I did was multiply 1 atmosphere times 290, and I got 290 Kelvin times atmosphere. So I just sort of combined the units together right now. When you're doing problems like this, it's super important to make sure that you don't get rid of your units and that you follow the units through the whole problem, because the units are going to help us see what cancels out where. Okay, but now we're ready to divide both sides of the equation by 273.15. So we're going to take both of them, both sides, divide them by 273.15. And then on the left side, I have P2 equals 1.06 atmospheres. So I took 290 divided by 273. And then on the right side of that equation, the 273s, they both canceled out with each other. And all I was left with was P2. If you notice, on the bottom left of my screen here, the 2 Kelvin temperatures will cancel out with each other. And the unit that I'm left with is atmospheres. So that matches up, because I was trying to solve for pressure, and atmospheres is a pressure unit. So if your unit doesn't match with your variable, then you know you've made a mistake. But this is the first example. Make sure you have all of this written down. And you got as an answer that the pressure 2 equals 1.06 atmospheres. And that makes sense, right? Because if we look back at the word problem, we increased the temperature. And if we increased the temperature, then the pressure also should have gone up, because pressure and temperature are directly proportional. Let's do another example. In this example, it says, at 72.0 degrees Fahrenheit, the pressure in an oxygen tank is 179.6 atmospheres. The oxygen tanks will rupture if they reach 272.2 atmospheres of pressure. At what temperature will that occur? So let's remember, if we think back to our steps on how to solve a word problem, the first thing that we're going to do is pull out all of our information and variables from the problem. So it says at 72.0 degrees Fahrenheit. Okay, so that's one temperature. And it says at that temperature, the pressure is 179.6 atmospheres. So those two values go together. One is pressure 1 and the other is temperature 1. But maybe you've spotted the problem. We need all of our temperatures to be in Kelvin. So at some point, we're going to have to convert that 72 degrees Fahrenheit to Kelvin. Okay, but let's find the rest of our information. The problem also says that oxygen tanks will rupture at 272.2 atmospheres of pressure. And then they want to know what is the temperature at which the oxygen tanks will rupture, right? So if the pressure final, or the P2, is 272.2, what is the temperature 2, or the T2? But also it's asking us to find that temperature in Fahrenheit. So we need to keep all of this information in our brains as we move forward. The first thing that we need to do is convert our temperature to Kelvin. So I went ahead and put all the work for that on the right of my screen here. So hopefully you remember how to convert between Fahrenheit and Kelvin. You use the formula that you have from your homework a couple nights ago. The Kelvin temperature equals, parentheses, Fahrenheit temperature plus 459.67 times 5/9. So then you plug in 72 degrees Fahrenheit, and then you solve your equation, and you should get 295.37 Kelvin. Having to convert temperatures is not going to go away. Just like you're going to be expected to be able to convert between pressure units, you're going to be expected to convert between temperature units. Okay, but now we've got our 72 degrees Fahrenheit. It's in Kelvin, 295.37. So that's our P1, and we've got our P1 and our P2. But it looks like we need to solve for P2. So let's go ahead and plug all of our values, all of our variables into the equation. And you should get 179.6 atmospheres divided by 295.37 Kelvin equals 272.2 atmospheres divided by T2. Okay, remember the next step is that we need to cross multiply and divide. So we're going to multiply 179.6 times T2, and on the other side we'll have 272.2 atmospheres times 295.37 Kelvin. Remember that 295.37 Kelvin is the temperature that we converted from Fahrenheit. So originally it was 72 degrees Fahrenheit, but we converted it into kelvins. Okay, now I've simplified my formula a little bit for you. Right? I multiplied 272.2 times 295.37. So the next thing that we need to do is solve for T2. So we need to divide both sides of the equation by 179.6. So let's go ahead and divide both sides of the equation by 179.6 atmospheres. Now on the left side, the 179.6 is going to cancel out, and we're going to be left with just T2. And on the right side, we're going to have to do that division in your calculator, but then The atmosphere units will cancel out with each other. We'll be left with Kelvin unit. And hopefully you got that T2 equals 447.7 Kelvin. But this isn't actually the end, because if you look back in the problem, it wants to know the temperature in Fahrenheit. And our work just told us the temperature in Kelvin. So we're going to need to convert back to Fahrenheit. And the work for that is shown in the bottom right. You have to plug in 447.7 for TK, and then you're going to have to solve. Right? You need to divide both sides by 5/9. Right? Dividing both sides by 5/9 is the same thing as multiplying by 9/5. And then you'll subtract 459.67 from both sides to end up with a Fahrenheit temperature of 346 degrees Fahrenheit. Wow, that was a lot of work. So let's double check that our answer makes sense. In the problem, we raised the pressure. And if we raised the pressure, then the temperature also needed to go up, right? If pressure goes up, temperature goes up. And it looks like, yes, our temperature did go up. It started at 72 and it ended up at 346. So it looks like we're doing good here, but this was a lot of math today and a lot of new concepts. So if you need to rewatch the video, feel free. But otherwise, we have homework over this topic, and you should spend the rest of time working on this homework. Good luck, and please feel free to email me with any questions.